Okay, so in this set of slides, I'm going to explain autoencoders. So this is another family of networks, and it's in fact closely related to these encoder-decoders that we've been talking about. Now, an important difference is that an encoder-decoder takes something as input like a sentence, produces another sentence as output, and that other sentence is different. But in an autoencoder, the idea is that we take something as input, and then the output is the same. Now you might ask, so what's the point of doing this? If we have the input, why are we trying to produce the same thing as output? The difference is that now the goal is not really the output, but something intermediate that we're going to calculate. Okay, so autoencoders are quite important for various tasks, including compression, denoising, obtaining a sparse representation, and also doing data generation. Okay, so if we do compression, the idea is that we might have some input that has a certain dimensionality, so it might be a very large vector, and now we want to compress it, so we want to map this into a vector that has a smaller representation. So this is useful, let's say, for image compression, video compression, also speech compression. So a lot of data, sometimes it's good if we can compress it, but when we compress it, we want to make sure that we don't lose information. So if after we get our compression, we can reconstruct what the input is, then it means that we haven't lost any information and everything is good. So this is where autoencoders become useful, because even though they reconstruct the input, that's not the goal, but on the other hand, this ensures that whatever we've computed as an intermediate representation still captures the same information as the input, that we haven't lost anything. Okay, so to be concrete, let's say that I've got an image that corresponds to a 2. And let's say that this image is a high-dimensional vector, and I want to compress that, right? So image compression is an important task. And now what we can do is simply feed this 2 to an encoder. I'm going to denote this by a function f, and then I get a compressed representation. So this is just going to be a vector of smaller dimensionality. That vector will have some values. It's not clear how to interpret those values per se, but the point is that it's just going to be a compressed representation. Now, I want to make sure that this compressed representation has not lost any information. So what I do is I try to reconstruct my input. If I succeed, then clearly it must be the case that my compressed representation has all the information of the input. Right? So this is why an autoencoder is often useful, because we're going to compute something intermediary, and then if we want to make sure that it captures the same information, then we must be able to reconstruct the input. Okay, so to make things clear, let me draw a picture, and we're going to start with a simple linear autoencoder. And linear means that we're just going to have a layer that will compute a linear transformation, and we can denote this by some weight matrices. So I'm going to have WF for the weight matrix of the function f, and WG for the weight matrix of the function g. Okay, so we've got x, then typically h will be some lower dimensional representation, and then we have x again, like this. In fact, x will typically be an approximation, so let me write this as x tilde. And now we have a set of weights, wf, for the function f that maps x to h, and there's wg that will map h to x tilde. Okay, so here we have that h is equal to wf times x, and then there's x tilde that is equal to wg times h. Okay, so when I work with an autoencoder, then, and it is a linear autoencoder, what I would obtain is essentially a computation like this. You see, I try to reconstruct x by multiplying x by wf and by wg. And now if I would like to make sure that this is close to my original x, then I can simply try to minimize some objective like squared loss, and then I can use backpropagation, in other words gradient descent, to obtain the solution. Okay, now for anybody who's familiar with linear algebra and also a bit of statistics, whenever we use the Euclidean norms, in other words the squared loss for this objective, and whenever we have some linear mappings, then it turns out that the solution to this is known as principal component analysis. So here the idea is that we could take our data, decompose it into what are known as principal components that correspond to components of maximal variation. And there's some techniques for doing this that have been well studied in linear algebra and also statistics. But here what we could do is simply use an autoencoder to essentially perform the same thing and find some matrix wg and wf that minimizes this. So it's equivalent. Okay, so principal component analysis is typically used to project data. Okay, the quality of those pictures are not great, but in any case, we've got data into some original space. So here, let's say that our space is in 3D. So this could be some space where I've got a first axis, second axis, third axis, and now my data contains points of different classes. So I've got some red points, some green points, some purple points, and so on. And then when I apply PCA, what PCA does is to essentially try to take my data and map it into a lower dimensional hyperplane such that I preserve as much as possible variations in my data. So you see, here we could imagine that there's a hyperplane that I could project my data onto, and then if I draw this hyperplane flatly on the screen, right, then my data would project in this way. Right? So principal component analysis is a good way to essentially take data into a higher dimensional space and project it into a lower dimensional space using a linear transformation. And then when doing this, we're going to try to preserve as much of the variation of the data, which means that in principle we could reconstruct as closely as possible the original data. So that's how these things correspond to each other. Okay, any questions regarding PCA? Yeah. Well, so here, if I have an autoencoder that has some linear mappings and I minimize Euclidean distance, it will give me the same solution as PCA.
Based on the objective of autoencoder, can we say that WG is just the pseudo-inverse of W?
That's right. So yeah, that's another important point, that WF and WG are essentially inverses or pseudo-inverses of each other, because whenever I multiply WG by WF, I would go from x to x tilde. If my x tilde is essentially x, then I now have exact pseudo-inverses. In practice, they're going to be approximate pseudo-inverses. Now, with an autoencoder, there would be no point if all we were trying to do is the same as PCA. The beauty of an autoencoder is that we don't have to restrict ourselves to linear mappings. Right? So here we can think of the function f as a general function, a nonlinear function, and same thing for g. So now if I generalize what I had on the previous slide to arbitrary functions, I get a similar expression. And now I can simply try to minimize Euclidean distance. And then the hidden nodes are going to correspond to a nonlinear manifold. So the intuition is that what we're really doing by computing some hidden representation here would be to essentially take our data and project it onto a lower dimensional space, but this lower dimensional space is not linear anymore because I allow myself to have nonlinear mappings. And so yeah, in this picture you see there's a manifold that corresponds to this S. I've got data on this manifold, and now when I apply F, it would be the same as going, let's say, from this 3D space in which there's a 2D manifold, and then projecting the data just on the 2D space where it would have the same effect as like stretching my 2D manifold to make it planar. Okay, so this is a simple example where we go from 3D to 2D, but more generally, you could imagine that your data lives into a high dimensional space, but really is within a lower dimensional manifold. And now what we're really doing here by computing some hidden compressed representation is to find perhaps what is that lower manifold that captures the data. And ideally, if we can reconstruct the input, it means that we found a manifold that captures perfectly the data. And now we're essentially exposing what is this lower manifold, lower dimensional manifold, with a vector representation that is compressed. And now we could plot this, and it would be essentially a space with fewer dimensions. Yeah?
From the second graph to the third one, you have unfolded the manifold like this?
Yeah, so that's how we can think about it, that you see I'm in 3D here, so I've got 3 axes, right? The data really lives into a 2D manifold. So now when I go from, let's say, a vector x of 3 dimensions to a vector h of 2 dimensions, it is the same as simply mapping every point into this 2D space. Now in this 2D space, obviously it's flat because it's just 2D, right? More generally, see, we're going to go from any dimensions to fewer dimensions, and it does correspond more or less to flattening this space into, I guess, a lower dimensional space. Yeah?
Here we map from, we know that our manifold's intrinsic dimension is 2D. And so if we have a autoencoder which is input layer is 3 and its hidden layer is 2, so we can unfold it. But if we have an autoencoder with input layer 3 but hidden layer of just 1, we will lose some information. My question is that is there any way to just capture the intrinsic dimensionality of the manifold in the data space to just adjust the
Yeah, very good point. So yeah, how do we adjust the dimensionality of H so that we capture precisely all the information and that this would be lossless, right? So I'm not aware of general techniques, so I guess this is where we'd have to look at perhaps techniques for structural learning. Well, I guess okay, here if it's just adjusting H, the dimensionality of H, we could imagine just doing a grid search over all the possible dimensionality of H and then trying them out and then seeing which one has the best reconstruction among the smallest H, right? So you could do a search like this. You could use cross-validation to ensure that you've got some form of generalization. But yeah, other than doing a search like that, I don't think that we have techniques that would automatically otherwise find what is the right dimensionality for H. Okay, so if we consider now the fact that we allow F and G to be nonlinear mapping, there's also no reason why they should be just one layer, right? So here we can have deep autoencoders. That essentially means that we have multiple layers before we reach the hidden layer, and then multiple layers to reconstruct as well. Okay, so just to illustrate, let's draw another graph. So for a deep autoencoder, so we might have X and H is here. And now we might have several layers. And we'll have X tilde here. Okay, so here I just drew several intermediate layers. Obviously, the number of layers can vary. And this would just allow us to construct some mappings that can be fairly sophisticated. Okay, so with autoencoders, what's also interesting is that we can also obtain representations that are not necessarily lower dimensional, but are also sparse. So sometimes what you want is not necessarily compression, but you want to impose some structure onto your intermediate representation. And one common type of structure is just to say, I want the representation to be sparse. So here, the idea is that in addition to just ensuring that there's a good reconstruction loss, you also want to add an additional term. You can think of it as some form of regularizer, but this term is where we impose the additional constraint, the additional structure. So here, NNZ stands for the number of non-zero entries of the vector produced by F. So here, this might not be something easy to optimize. So in fact, it's well known that in optimization, if we want to make sure that we have a sparse representation, it leads to a non-convex problem. So the optimization will not be easy in general, but still we can formulate the problem. It doesn't stop us from applying some gradient technique and seeing what happens. Now, if we want to preserve convexity, an approximation to this is what is known as L1 regularization. So simply minimize the L1 norm of the output of F. And even though this does not guarantee that we minimize the number of zero entries, in practice it often does. Okay, so then we could have something that is at least the second term here would be convex, and then the first term, it depends on what F and G would be. So that's often what is used in practice. Okay, as a concrete example, let's say that we also want to use an autoencoder for denoising. So let's say that we have some input X, and now in practice, what we tend to receive are perturbed versions of this. So it's been corrupted by some noise. and now we'd like to recover x. So what we can do is simply feed x tilde as input and try to reconstruct x. So earlier I mentioned that we start with x, and then when we do the compression, we might not be able to reconstruct x exactly. We're going to get x tilde. But now in the denoising case, it's sort of like the other way around. We're given a perturbed x tilde, and now there's a clean x that we would like to reconstruct, and that's what we would do. Okay, so we would have both x and x tilde. We feed x tilde as input, and now we try to produce an output that matches x. So we can use something similar to what we've done before. We can also add some regularization term, and then you might obtain results that look like this. All right, so we've been talking about autoencoders, and so far all of our autoencoders have been deterministic, and that's the most natural thing to do with a neural network, right? So here again we have an encoder that will take some input and then produce some intermediate representation, and then there's a decoder that will after that reconstruct our input. So this is natural, but it turns out that we can also consider probabilistic or stochastic autoencoders, and these are going to have some interesting properties. In particular, they're also going to allow us to generate data. Okay, so what do I mean by a probabilistic autoencoder? I mean that the encoder is essentially a conditional distribution over the intermediate representation, and then the decoder is going to be again a conditional distribution, but this time with respect to the input that we're trying to produce. Okay, so here when we design probabilistic autoencoders, if we want to have some conditional distributions, what it means is that when we design our neural network, we just need to make sure that the last activation function in the output layer is going to produce some values that can be interpreted as parameters of a distribution. So for instance, we've seen how to use the sigmoid to encode distributions over binary values. So for instance, if my data consists of binary vectors, so if x consists of binary vectors, then it would make sense to have a decoder that essentially has a sigmoid output layer in order to have a distribution over those binary values. Now, if I don't have binary data, but instead I have categorical data, then I can also use a softmax output layer. And if I have real data, then I can simply use a linear activation function. So in other words, linear units, which means that there's no activation function, or if you prefer, the identity activation function. And the idea is that those linear units, we can think of them as producing parameters, let's say, of a Gaussian distribution. So a Gaussian is parameterized by a mean and variance. And now the mean can be any real number. So if I have a linear unit, then it might produce any real number, and that's good. For the variance, if we consider the square root of that, that could be any real number. It could even be a negative number, so it would not be exactly a standard deviation, but I could think of it as like producing some number, possibly negative, such that when I square, then I get a positive real number that I can interpret as the variance. So the idea is that those types of units, if they're structured in the right way, they can be used to essentially encode conditional distributions, and then we'll have a probabilistic autoencoder. Okay, just to make sure that we all understand, let me draw on the board what the architecture would look like. Okay, so we have our input x, then it will determine some hidden representation h, and then we have our output, here our output, we would like it to be x again, but just to distinguish it, let me use x tilde to indicate that this is, generally speaking, going to be some representation that is an approximate version of our input x. Okay, and here I drew this as a probabilistic graphical model. So in the case of a probabilistic encoder, I'm going to think of x as a random variable. I'm going to think of h as another random variable. And I'm going to think of my output x tilde as yet another random variable. So here, in this probabilistic graphical model, the arrows would indicate conditional dependencies. So I would have the probability of h given x. And now we have some parameters. In this case, let me use WF to indicate that the weights are essentially parameters of this conditional distribution. And then same thing for x tilde. So I'm going to have the probability of x given h, as well as the parameters WG. So my decoder is a conditional distribution of this form. Okay, and I guess here I should put x tilde. In general, we won't necessarily be distinguishing between x tilde and x. Now, from a probabilistic perspective, we would like x tilde and x to be the same. Generally speaking, they won't be, so that's why I'm using x tilde, but often you'll see that x gets used as well. Okay, so that's what we have. And now, if I want to produce an output here that is with respect to binary vectors, then I can use a sigmoid. So a sigmoid activation function will give me a Bernoulli distribution. If I use a softmax, then I'll have a categorical distribution. And then if I use linear, so I guess, okay, if I talk about activation functions, this should be the identity activation function. So in other words, no activation function, just a linear mapping. Then I can get any real number, and then I'll be able to interpret this as a Gaussian. Okay, so these are examples. Okay, and now just to be clear, let me draw, let's say for the sigmoid. So here I could have x, which is my vector of input. Then I might have several intermediate layers. And then here I will have, let's say, several sigmoids. Okay, so here those sigmoids are essentially giving me the probability of h given x and wf. Okay, where h would be binary. Okay, and then after this, I might have a few other layers. And then the output would also be with a bunch of sigmoids. And now we get here the probability of x given h and wf, where here again x would be binary. Okay, so in general, we think of x as a vector, we think of h as a vector. In both cases, if they're just going to be vectors of zeros and ones, then what would make sense is that I simply compute a distribution over h, and then based on that, compute a distribution over x. Okay, so this is for sigmoid. If I want to have a Gaussian, I can do something similar. So I'm going to have x as input. Then here let me put sigmoid, actually let me use mu. Okay, so we have here, it's going to be a Gaussian distribution over H based on some mean mu, and here some variance sigma square. Okay, so here just to be clear, these sigmoids are really the sigmoid function, and these sigmas are really just the square root of the variance. Okay, so they don't mean the same thing. Okay, it's just that we have the same symbol that happens to be used in two different contexts. Right? So these are sigmoids, and these are just sigmas that indicate the square root of a Gaussian distribution. Okay, so, and here just to be clear, let me add that this depends on WF. Okay, and then we would have a few more layers, and eventually the output. Here, in fact, to be clear, let me make the output fairly large. So I'm going to have mu sigma, like this, mu sigma. If this is of size m, so if this has m dimensions, right, here I'm going to have this of size 2m, simply because for every dimension here, I'm going to have a pair of a mean and square root of the variance. Okay, and then this is going to give me again a Gaussian in x based on h, as well as mu sigma and wg. Okay, and this one here should depend on x. Yeah. Okay, so based on this, what's interesting is that now we can potentially use an architecture like this as probabilistic to generate data. So normally with a deterministic autoencoder, what happens is that you take some data point x as input, you produce an intermediate representation h, and then the decoder is really something that takes, I guess, some embedding and then generates a data point. Now, if we want to generate new data points that are similar to the data points that we have in our training set, the beauty of having a distribution is that perhaps I could sample from some distribution over my intermediate representation H. Let's say that I make this distribution a Gaussian with mean 0, variance 1. So it could correspond to just sampling points within some space. And then every point here, after this, I could use it to generate a data point, which might be a face in an image. So let's say that I'm training here a probabilistic autoencoder with faces. So these are specific types of images. And I'd like to be able to generate new faces that are similar to the ones that I have in my data set, but different. Okay? So the beauty is that, you see, here, in principle, I can simply sample from a distribution over my hidden representation. And then for every h, now I've trained in my network a decoder that can take some h and then produce some output. Okay, so when it produces the output, it's going to produce a distribution over images, and then I could sample that and obtain an image. Okay, so I guess, yeah, one nice aspect of these probabilistic autoencoders is that they do facilitate the generation. Now, there's one problem in what I have on the board here, or sorry, on the slide here, is that I need some distribution that I can sample from. And if I just go back to the board, in this picture here, you see I would have some faces that correspond to some input data point x, and then they all get mapped here. Obviously, every h that I can generate from x is going to be a proper embedding of that image. And then if it captures all the information, then I can generate, again, my original image. Now, if I want to generate new images, what I could do is try to make sure that when I embed my images here, they all get embedded into some space, such that if I take points that are nearby, right, they don't have to be the exact same h as those that correspond to my input x, but just something that is nearby, then I have a decoder that then can generate an image based on that, and then that would lead to a new image, a new face. Okay? So now in order for this to work, I'll have to make sure two things: that I can sample from here some h's, that some embeddings that do indeed correspond to some proper data point into my image space. So therefore, I need a distribution that allows me to sample. And the distribution that I have here is a distribution that is conditioned on x. The problem is, if I want to generate data that is not exactly x, right, then I don't want a condition on x. So here, this autoencoder could be trained to start with x, produce an h, and then have a high likelihood of producing an x again. So this is trained to optimize that. The problem is that now if I want to generate a new image, if I start with x, I generate an h, and now by sampling, let's say I generate an h, and then again I generate an x by sampling, chances are my new image is going to be very similar to the one that I started with, right? So it has the issue that I might not be able to generate really brand new images. I'm just going to be able to generate images that are similar, because effectively this neural network has been trained to reconstruct my original image, and is going to try to do this by remaining as close as possible. So if I want to be able to generate new images that are not necessarily just slight variants of my input data, then I will need some mechanism to be able to sample directly an h here, and then generate after that an image. So that's what we're going to see in the next set of slides. But before I go on, any questions regarding this? Okay, very good. So yeah, so let's move on to the next set of slides.